Good morning to all of those west of the Mississippi, and good afternoon those on the East Coast. I'm Rick Carney, coordinator for the Great Basin Landscape Conservation Cooperative. For those of you who might be new to the idea of a LCC, we are a partnership among public and private groups who are working together to meet large conservation challenges across the 5-state Great Basin region. We have supported a variety of conservation projects on high priority topics. This series highlights a few of these projects, plus more. We hope that these webinars can provide a platform for discussion about research and its application in the Great Basin. We will keep today's presentation relatively short, about 30 minutes or so, and reserve the second half of the hour for questions and discussion with today's presenter. Since there are quite a few people on the webinar today, we ask that you type your questions as they arise, and I'll provide you instructions in just a second. Then we'll read out your questions for the speaker at the end of the presentation. Today's webinar will be recorded and available on our website in just a day or so. If you look on your screen, you'll notice a small collapsed control panel in the upper right-hand corner. By clicking on the small orange arrow, you can expand this control panel. Once you do, there's a space down below for typing in your questions. Simply type your questions there in the chat area and press send. Then your question will be sent to us and we'll respond to that at the end of the webinar. Now, I would like to introduce today's speaker, Dr. Bruce Roundy. Bruce Roundy is a professor in the Department of Plant and Wildlife Sciences at Brigham Young University in Provo, Utah. He holds a PhD in range management from Utah State University and has master's and bachelor's degrees from the University of Nevada, Reno. At Brigham Young, Bruce teaches undergraduate and graduate courses in rangeland management and improvement, restoration ecology, and watershed management. He has been researching topics related to rangeland restoration for over 40 years. I would like to, at this point, turn the controls over to Dr. Bruce Roundy. Bruce?
Okay, thank you very much, Rick. I'd like to thank Rick Kearney and John Toll with the Great Basin Landscape Conservation Cooperative for supporting this work, and also Emma and Liz for helping out with the presentation. Also, this work is supported by SageSTEP, which research project I'll be talking about quite a bit today, and Brigham Young University. I'd like to recognize my SageSTEP Associates that you see listed there from a variety of universities, the Forest Service, and USGS. This has been a long and very fruitful project, initially funded by the Joint Fire Sciences Program, and now funded by the Bureau of Land Management, National Interagency Fire Center, and of course the Landscape Conservation Cooperative. I'll tell you a quick story. When we first set up SageSTEP, we were planning a prescribed fire treatment and some other treatments over on the Onakee Mountains managed by the Salt Lake office of the Bureau of Land Management. And with a meeting with their resource managers, one of those wagged her finger at me and said, "Okay, Roundy, if you convert this land to cheatgrass, you'll be responsible for it." So one of the big problems we have when we get fuel control projects going, which we want to do to suppress high severity wildfire, fuel control is one of the things we can manage, is we can end up with weed dominance, and every natural resource manager is concerned that that could happen. So, for example, we had a prescribed fire at Scipio. We got a lot of cheatgrass. We had one at Stansbury, got a lot of cheatgrass. But at the Onakee site, where I got my finger wagged at, we got a lot of perennial grass response and not a lot of cheatgrass. Even though there was cheatgrass in the area in these swales, it didn't dominate the site. So that's one of the things that you run into, is this between site variability in response to vegetation treatments. So let me just describe the regional SageSTEP experiment. One reason it was funded by Joint Fire Sciences was we really wanted to see if you could get similar responses to fuel control treatments across a wide range of sites. And so there were two major experiments. One was in Wyoming big sagebrush, and the other one was where pinyon and juniper trees had expanded into sagebrush. The big sagebrush treatment, our experiment had 6 sites for woody fuel control treatments. You can see listed there. And overlaid on that were 2 herbaceous fuel control treatments to control cheatgrass, where a masopic or a plateau was applied. The woodland expansion experiment had 11 sites, 3 to 4 fuel treatments, including untreated fire and mechanical. Across the region, we cut and dropped, and in Utah, we cut and dropped and also had plots where we masticated or shredded the trees to compare, because we do a lot of that in Utah. And you can see from this map, we had sites scattered across the Basin and Range province. You might have to fudge a little to say some of these are in the Great Basin, but similar topography with fault block mountains and alluvial valleys, all the way from Washington down to southern Utah and across Nevada, Oregon, and some sites in Idaho. As part of this, we were encouraged to install soil temperature and moisture stations, and so we did that. We have over 178 stations that we installed on 4 to 5 treatments across the region. In the sagebrush experiment, we installed them on low and high perennial grass plots. The woodland, we installed them on 3 expansion phases. By that I mean phase 1 would be where trees are just starting to come into the sagebrush steppe. Phase 2 would be where trees and the understory shrubs and grasses share cover. And phase 3 is where the trees are now dominating. We installed on 4 microsites. A microsite might be like the edge of a tree canopy, the edge of a shrub canopy, an inner space, and next to a tall grass, and so on. We installed at 6 steps, the upper 30 centimeters, where a lot of the competition for moisture and nutrients is, and then some deeper ones. We recorded hourly averages and came up with 29 derived seasonal variables that we could relate to our responses. It would help us sort out why things happened the way they did. Much of the initial SageSTEP results were reported in Rangeland and Ecology and Management, a special issue in September 2014. Other papers were reported in other journals. I've listed a bunch of them here. Those were like the 3 to 4 year results. Rachel Williams and I and others recently published 6-year results on the woodland expansion that's in Rangeland Ecology and Management, 2017. I'm just going to briefly, generally summarize the response we got in vegetation here, but there's a lot more details in these publications. On the sagebrush experiment, when we used prescribed fire, it definitely decreased the woody fuels well. It decreased perennial grass cover initially, then it came back to be equal to the control or untreated. Cheatgrass was highly variable, but we tended to get quite a bit of cheatgrass on the burn treatments on the sagebrush experiment. The mow decreased woody fuels also. It was set to control about 50% cover of the sagebrush. Perennial grass didn't change it compared to the untreated, and cheatgrass was variable. Some sites had a lot of cheatgrass, some didn't on the mow. Tebuthyron, didn't see a big difference, but on some sites we did kill quite a bit of the sagebrush. The masopic set back the perennial grass and cheatgrass quite a bit. And Dave Pike reported on that in the 214 issue. Ben Rao's study concluded that the treatments increased available nutrients, and drier and sandier sites had more cheatgrass. but I think he only studied about 4 of the 6 sites when he reported that. On the woodland experiment, fire definitely controlled woody fuels best. It decreased perennial grasses initially, but by 6 years after treatment had increased perennial grass cover above what the untreated was, and it increased cheatgrass on most sites, but highly variable. The cut and shred treatments, the woody fuels depends on what you did. If you cut the trees, you mainly put all the fuel right on the ground. If you shred the trees, you take what we call the 1,000 and 100 hour size classes, and you shred them down, and they become mainly 1 and 10 hour size classes, which really can aid in fire suppression. Doesn't get rid of the fuels, but it aids in suppression. The fire will drop from a canopy right to the ground, and you can put it out. These mechanical treatments really increase the perennial grass cover. Cheatgrass cover increased a little bit, but it was highly variable. Some sites had a lot more than others. We also want to reiterate from the expansion study, the tree expansion study, when you have higher pre-treatment tree dominance, like phase 3, you really increase the woody fuels. You have decreased understory. For example, if you have 20% tree cover across our population of sites, you'd already lost 50% of your sagebrush cover. These treatments increased available nutrients in soil water, and they tended to increase post-treatment cheatgrass. So that's just, briefly what we found out there. Now, Gene Chambers and Rick Miller have emphasized, and Dave Pike also, that perennial grasses, if you want good resistance to invasive weeds like cheatgrass, you need to maintain perennial herbaceous cover. But that relationship will vary greatly within a site and from site to site. For example, at the Roberts sagebrush site, here I've graphed sagebrush burn, mow, and herbicide. Cheatgrass cover on the y-axis, perennial herbaceous cover. You see a relationship here, but a lot of scatter. You can get a wide range in cheatgrass cover for a given perennial herbaceous cover. If you just look at the Roberts sagebrush burn, you get enough perennial grass that you can see a nice relationship where you get 50% perennial herbaceous cover, you reduce cheatgrass cover to about 10%. But if you look over on the sagebrush mow plots, they didn't have enough perennial grass to create this relationship. So this suppression of cheatgrass by perennial grass can be highly variable. And these slides kind of illustrate this. Here at the Saddle Mountain sagebrush site, you see a lot of perennial grass response to the fuel control treatment, but look at all the cheatgrass in the interspaces. If you go down here to the Stansbury site, a woodland site in Utah with the highest cheatgrass cover of any of our sites, where you have patches of perennial grass, you have very little cheatgrass, but then you have a lot where you don't have high patches of perennial grass. As is also illustrated in this perennial grass patch in Tinnick Valley. This is the Marking Corral site, and it's got a lot of bare ground where we did cut and drop. And you don't see a lot of cheatgrass in the bare spaces in between. Yet, just across the fence where the burn plot is, you see quite a bit of cheatgrass. So there's a lot of variability between sites and this relationship of cheatgrass with perennial grass. This has been organized really well into a management framework by Gene Chambers and then Rick Miller and Dave Pike, where they've related the potential to have cheatgrass or perennial grass dominance to elevation and soil moisture and temperature regimes. And Wyoming sagebrush is best adapted to cheatgrass. It has lower perennial herbaceous productivity, and after a fire, it's harder for the perennial grasses to come back because it's drier and warmer. When you get into the pinyon juniper, these are a little bit more resilient, especially if you have mountain big sagebrush. And then you get much more resistance to cheatgrass and resilience as you get higher elevation because the perennial herbaceous component can come back after a disturbance better. It's more productive, it's more competitive. Some of the shrubs can sprout back, like snowberry and so on. So we're mainly going to talk about this right here. And again, this resistance and resilience, resistance being able to resist cheatgrass invasion and dominance, resilience being able to come back with perennial shrubs and herbaceous plants that we desire after disturbance, varies with your elevation and your soil moisture temperature regimes. So we've done that by association, quite well laid that out, and it generally works pretty well. But we'll find there's a lot of variation in here. So you get to this idea of fundamental niche. Where is cheatgrass best adapted? Where does it germinate best, get the highest seed production, and can reestablish and grow every year? What soil moisture and temperature best suits that versus the realized niche where cheatgrass is held back by competition for resources. One thing we know for sure, if you've got warmer sites with cheatgrass before treatment, you're going to have a lot of cheatgrass after treatment. The Stansbury site illustrates this. These blue dots illustrate are the untreated, the green dots are the burned or mechanically treated where we took down the trees. We definitely got an increase in cheatgrass, but we had a lot there to begin with. How does this work? I'll just briefly talk about that. Disturbance on a pretreatment community results in a post-treatment community, which is a function of the pretreatment community. You have a lot of cheatgrass there to begin with and very little perennial grass. You have a lot of cheatgrass and low perennial grass after your fire or mechanical treatment. But disturbance also affects as it occurs on the pretreatment microclimate, will result in a post-treatment microclimate and resource pool. And that's mediated also by the site characteristics, the elevation, the slope, the precipitation, the climatic conditions. This is really illustrated very well in this burn at Scipio. Here's our burn, the edge of our burn plot, and we got a lot of cheatgrass here and practically no cheatgrass when you step away from where we burned. Now that's not always that clear, but at Scipio and Marking Corral, that was very clear. We definitely changed something by burning that helped the cheatgrass here. Now, speaking of the resource pool, that's mainly the upper 30 centimeters. That's where most of the spring soil moisture is for growth. That's where the nitrogen is for growth. And in April and May, when there's a lot of soil water, the nitrogen can flow to the roots. Perennial plants will deplete that. Annual plants will deplete it in the upper 30 centimeters, but not lower, because their roots don't go down that far. But this is just to illustrate that soil moisture is really key to growth during that short window when there's spring and winter soil moisture and warm temperatures in April and May. And then by June, July, the soil moisture's gone. The nitrogen can't flow to the roots. Growth is over. Plants might still be green, but they don't grow much. Okay, so if you take out the trees or take out the shrubs or decrease the shrubs, you should increase soil water availability. And we found that not so much in the sagebrush experiment, but definitely in the woodland experiment. And for example, up to 8+ years after treatment, we're finding 10 to 20 days more available water if you took out the trees at phase 3 where they were dense trees. So you're making a lot of available water, available to the plants that are there to use it, be it cheatgrass, perennial grasses, or shrubs. We also found somewhat increased soil temperature, not a lot, but somewhat, by burning. And this can greatly increase the germination potential of seeds and some research done by Nathan Klein compared to no treatment or mechanical treatment. So burning really can stimulate stand renewal through seedlings. Also, you can get some soil water repellency from burning. I won't talk much about that, but that can sequester nitrogen up here. It breaks down over time after the burn, and it could be reasons we see patterns of cheatgrass and perennial grasses coming in later under tree mounds after burning. And we see some increased nutrient availability. For example, Kurt Young showed in a detailed study of treating phase 3 or dense juniper. It increased the time of water availability up to 6 weeks in the spring. It increased the nitrogen that the plants depend on for growth through all seasons. This is a substantial increase in nitrogen moving through resin bags, which mimic roots. And that in turn increased biomass of both cheatgrass and blue bunch wheatgrass seedlings. So you get this bonus of resource when you do fuel control treatments here. But what explains the site differences? So you do a treatment, you get a bonus of resources, but what happens really can vary with site. So I've arrayed here all of our SageSTEP sites, all 17 of them, and with the data that I have 6 years post-treatment and also pre-treatment. And this is for the burn plots, and this is cheatgrass cover. And we go from no cheatgrass at the 7 Mile site to a lot of cheatgrass at Stansbury. And some of these that had a lot of cheatgrass to begin with, before treatment, had a lot afterwards. Some didn't have much to begin with and had a lot afterwards. You know, like Marking Corral, South Ruby, and Greenville. And we'd really like to be able to predict what they're going to do. So mean annual air temperature and October to June precipitation are graphed here. So these sites array out, you know, across a range of these abiotic variables, but trying to correlate these two variables with cheatgrass cover had very little predictability. That just didn't work. Maybe if we did it seasonally, it would. But what we decided to do was look at our soil climate from our soil moisture and temperature. Now, these graphs are a bit busy, but they're fairly simple. We ordinated our vegetation using an ordination program. So these are axes. So here for the sagebrush sites, these are dots that appear down in this kind of, these two quadrants have quite a bit of cheatgrass or other annuals. Sites that were more over here had more perennial herbaceous cover. Sites up here had more bare ground. Sites over here had more shrub cover. And then we correlated these ordination scores with our soil moisture and temperature variables. So what we basically found out, and the correlations weren't great. Maybe our R-squared values were 30% or so, but perennial herbs were favored by sites with wetter winters and warmer early springs, whereas cheatgrass was favored by warmer falls, winters, and early springs. Over on the woodland sites, we had a similar ordination, only cheatgrass and annuals are up in this part of the graph. Perennial herbs are over here. Annuals were more favored by warmer, wetter falls and warmer late springs. And perennial herbs were favored by wetter winters and early springs. On both these diagrams, we've graphed the average for the treatment. So you see the burn tended to create a little bit warmer and more cheatgrass conditions in the sagebrush and also the mow. And here also in the woodland, you got a little warmer and more favorable cheatgrass conditions with the burn, but more favorable perennial herb conditions with the mechanical treatments. So that was pretty neat. And we explained maybe 80 to 90% of the variation in the vegetation, but the correlations with the environmental variables were pretty low. So we went to what we called partition decision tree analysis, and this takes a variable like cheatgrass cover and it relates it to categories of the abiotic variables. And this sorted out pretty interestingly. Our first breaking point was late spring degree days. So if we had warmer late springs, we got more cheatgrass than if we didn't. Okay, quite a bit of difference there. These are cheatgrass cover values. And if we had late spring warmer and fall wetter, we got even more cheatgrass compared to if we didn't. And if we had less freezing in fall, we got the maximum cheatgrass. So late spring warmer, fall wetter, less freezing in fall, we get a lot of cheatgrass. On the other hand, if we had cooler springs, but fall was warmer, we got more cheatgrass. If fall was cooler but wet and not too cool, we got more cheatgrass. So there's compensations here, but the big thing is if fall is wetter and warmer and it's warmer in the spring, you're going to tend to get more cheatgrass. It's better adapted to those conditions. Sorry. We also did a partition analysis on the perennial herbaceous cover. Consistently wet winters and springs produced higher perennial herbaceous cover, or if it was drier, minimal spring freezing produced higher perennial herbaceous cover, and if we had cooler falls, more perennial herbaceous cover, whereas warmer falls would favor cheatgrass. On the other hand, if we had drier, less consistently wet winter periods, if we had a wet or warm early spring, we'd get more perennial herbaceous cover. So you can put these both together and come up with a bit of a scheme of what favors cheatgrass resistance as far as climate, okay, soil climate. So if you have winter winters and early springs, that really favors perennial herbs. If that's coupled with cooler springs and cool, dry falls, that's hard on cheatgrass, and so that's your sites are going to have the highest resistance to cheatgrass. But if it's coupled with warm late springs and warm wet falls, then your cheatgrass resistance will be intermediate. On the other hand, if you have drier winters and cooler springs, that disfavors the perennial herbs. If that's coupled with cool springs and cool, dry falls, that doesn't favor cheatgrass either. So you kind of have intermediate resistance. On the other hand, if it's coupled with warm late springs and warm wet falls, you're going to have the lowest cheatgrass resistance. So does this fit with the ecology of cheatgrass? I've kind of gone to the literature and looked at surveys of what climatic conditions favor cheatgrass. So this is kind of a list of that, as well as relating to the results from our study. Oh, and I see we're almost at 30 minutes, so I need to move along here. So warmer equals more cheatgrass if the soil water is available. More summer rain equals less cheatgrass, as perennial grass is favored, and you get more of that as you get higher elevation in the Great Basin. Cheatgrass is best adapted to fall, winter, and spring precip with dry summers. Spring, summer, and annual precipitation, as well as winter temperatures, have been shown to be the best indicators. In the end, Wyoming big sagebrush ecosystem is just really well adapted for cheatgrass. Cheatgrass germinates with fall rains and most springs, but cooler temperatures will limit its seed production. It can have highly variable growth, seed production, and germination on climatically marginal areas. On a warm year, you'll get more cheatgrass. It'll go out on a cooler year. You're really tied up with this dominance dependence on fire cycles, and it has a highly flexible response to nutrients, water, and temperature within its range. What are the predictions for global climate change? Bethany Bradley and others have written some excellent articles in this new book on exotic brome grasses that's available on the web. And she kind of concludes that cheatgrass will expand where summer soil moisture decreases. Its dominance will mainly increase within its current range of adaptation. It could go up a little in elevation, but most people don't think it'll do a lot that way unless it gets quite a bit warmer. But warmer and drier within its current adapted range may result in more cheatgrass fire cycle problems. Well, what do you do about it? I would refer you to the previous webinar on cheatgrass control. We're looking for a good way to do restoration, because in the Wyoming sagebrush, you're going to have cheatgrass, you're going to have fire, and it's not going to be what you want. If we do have good perennial grass, we should manage grazing by resting or light to moderate use in the growing season. That's really critical. We know those principles. In the Wyoming sagebrush, you have traditional ways of herbicide or fire and mechanical treatment and then seeding. But the trick is getting consistent establishment in the Wyoming sagebrush zone with seeding, with fire rehab. I would just say follow the principles of revegetation outlined in many guidebooks and books, and I'll show some of those guidebooks in a minute. On the expansion woodlands, it's obvious that if we cut or shred, we do mechanical treatments at phase 1 and 2, we can reduce our fuels. We'll have enough grass and shrubs to be more resistant to cheatgrass. If we have to treat phase 3 woodlands, we should seed or shred. We've shown in a study of mastication and seeding with Jordan Bybee that you can get pretty good success with that. When you have fires, wildland fires, follow the principles of revegetation here. It will make a big difference. Just a brief word about sagebrush renovation. We just completed a 10-year study, actually by Evanston, Wyoming, and it had very little cheatgrass on the site, but we compared aeration, meadow aerator, chaining, one-way and two-way harrowing with disking and imprinting. And you can really change your community composition of sagebrush, Wyoming sagebrush. If you have a lot of cheatgrass, I don't know if I'd recommend this without emphasizing revegetation. But what this shows is the untreated stays as kind of pretty stagnant sagebrush with limited perennial herbaceous. If you go in and do most of these treatments, it'll knock back the sagebrush a little bit and increase the residual perennial grass, but you won't get this dark green, which is the seeded perennial herbaceous. You have to do quite a bit more disturbance and really knock back the sagebrush to get more seeded success. And here we really increased the perennial herbaceous component, but the cost was at reducing sagebrush. So it's hard to get everything you want. And again, this site had little cheatgrass. It might have turned out quite differently if it had less than 1% cheatgrass. Masticate early to retain your shrubs and best retain your resistance to cheatgrass. I'm going to skip that slide due to time. Management and restoration guidebooks, there's a lot of them out there available on the web. This is a classic. The rest of those kind of follow the same guidelines, maybe with some updates with our new tools and remote sensing and so on. These are coming out. This one just came out by Dave Pike recently on dealing with different site conditions and restoration principles. Highly recommended to follow these guidebooks. Here's some promising technologies. You had a webinar on biocontrol. Susan Myers worked on that for years, and now others are getting into it. One thing I find to be the most innovative thing in 40 years of revegetation research is what Matt Madsen's doing with seed coating. They'll deactivate herbicides, so you could seed after applying plateau or something else. You can reduce water repellency. You can deter seed predation from rodents, which is a big problem on some sites. You can delay or speed up germination to increase seedling survival with abscisic acid and gibberellic acid. There's some 60 freeze-thaw periods on a typical sagebrush site between October and March. And that's hard on seedlings. So a lot of field studies going on with Matt, who's here at BYU, and we hope that results in some more success in the Wyoming sagebrush type. In conclusion, Sites vary in their potential for perennial herbaceous and cheatgrass cover, but cheatgrass, frankly, is adapted to a lot of Wyoming big sagebrush and many tree expanded sites, even into some of the mountain sagebrush. So you have potential for quite a bit of cheatgrass, maybe 10 to 20% cover on many sites. Best thing to do is maintain resistance and resilience by maximizing your perennial herbaceous cover by those approaches that I mentioned. I think I'm through at 35 minutes and I'm ready to take questions.
Thank you very much, Bruce. That was an excellent overview and summary of your work. Realizing we have a limited amount of time, I very much appreciate how much you were able to pack in there. Lots of good information. At this point, I'm going to turn it over to Emma and Liz up at Enviro Issues to read aloud the questions we received.
Thanks so much, Rick. We have actually only received one question, and it was about whether the slides from today's presentation will be available after the webinar, and they will be. We'll be publishing a recording of the webinar and the slides on our website, and everyone who registered for the webinar will get an email when those are available. But I have not received any other questions yet, so just a reminder, if you do have questions for Bruce, please type them in the questions section of your dashboard, and then I will be able to read those out. And we can wait a few minutes to see if any come in. Bruce, I know there were a couple slides that you did have to skip over or kind of truncate because of time. So if you did have any other comments you wanted to make, we can do that while people are typing in any questions they may have.
Okay, I'll just go back to this slide. What this does is show the cheatgrass to tallgrass cover ratio. So if this is higher, that means you got more cheatgrass, you're getting more proportional cheatgrass and tallgrass after your treatments. Graphing 3 and 6 years since treatment on our burn plots for the woodland study. This is an index of tree dominance, so the trees were much denser, higher cover up here. What it basically shows, if you burn, you're getting an increase in cheatgrass across the region, especially where you wait to treat when the trees get very dense. And that's because you don't have enough perennial grasses to suppress them. On the other hand, if you cut or masticate, very similar, you get a much lower cheatgrass to tallgrass cover. In other words, it seems like the perennial grasses are better winning the battle. But even if you wait to cut or masticate till high tree density, it's going to be harder for the perennial grasses to dominate the cheatgrass. So just to emphasize, in expansion zones, treat early. Mechanical results in less cheatgrass than burning. One of the problems with mechanical is the trees do come back and you have to go back in and retreat. We're seeing that happen now.
Thanks, Bruce. We did get one question typed in, and it is, do you have an estimate of increased costs as a result of seed coating?
I wish I did have that, and I can ask Madsen about that and get back to that. Understand that seed coating is at the developmental stage. We see some promising results in the laboratory, but we've got to prove it in the field before we really get into production of seed coats. They use it a lot on golf courses and stuff, but we've got to develop good, sound site field research to show that it's working. And we currently do that. We have a Joint Fire Sciences funded program that's looking at rodent deterrence, timing germination, and they have a lot of plots seeded this fall. So it's a little premature to jump it ahead to production, but there are some figures, and I'll get back to the questioner on that one.
Thanks, Bruce. We had a,
yeah.
Oh, go ahead, Rick.
I had a question of my own, and if we have time, I'd love to jump in right here. I wonder if you could speak for a moment about the relative efficacy of individual post-fire treatments versus multiple treatments and the timing of those treatments?
Yeah, that's a really good point, Rick. Dr. Davies up in Burns, Oregon with the ARS unit, Kurt Davies, has shown that you get a lot more success knocking back Medusa head if you burn it and then treat it with an herbicide and then revegetate. So if you're going to do restoration in Wyoming sagebrush, you really have to get pretty good control and then revegetate to keep the, the annual invasives back out of there. So some of these approaches are discussed in guidebooks. The Wyoming sagebrush is tough. Some of Dave Pike's work shows that fire rehab there is often not successful. Sometimes that's because it's just too dry. Sometimes it's because people didn't follow the principles of revegetation, seed something that had proven success, and cover the seed properly. Is that what you were asking me about, Rick?
Yes, as well as the timing. I recognize that often we don't have the flexibility to either postpone the onset of our post-fire treatments due to policy level guidelines. Other times we do get lucky with the right weather conditions post-treatment. So I was wondering if you have comments there.
Yeah, so that brings up maybe another item I should have mentioned, and that is Stuart Hardigree with the Agricultural Research Service in Boise and Colorado has put together a group that's looking at short-term forecasting. And the whole idea is that if you had a wet year, you would definitely seed more natives because you'd have more of a chance of getting a take with your natives. But if you had a drier year, you'd maybe seed more introduced species that are more aggressively established under marginal conditions. So there is some research going on there. Stuart's worked on this for years and years, and he's brought in weather modelers to the problem. And it'll be interesting to see what progress they make with that. For the fire rehab people, they just need to have a good plan in place before the fire even occurs, and many of them do, so that they can act quickly when the fire does occur. And that kind of brings up another thing. Some people say, well, let's don't bother these trees. Let's don't take the trees down where they've been baited. Let's just leave them there. But when you choose not to reduce your fuels, you may choose to let fire be your treatment. That happened over on the Stansbury Range. We treated some small areas experimentally. The resource manager wanted to treat a large area. That wasn't going to happen due to environmental concerns. 2 years into our study, a fire came along and burned 44,000 acres in 2 days. That became the treatment. Then you're really left with doing fire rehab. That's what you have to do, when maybe you could have gone in and mechanically treated and had better success. So there are constraints to doing the right thing at the right time sometimes.
Bruce, we received one follow-up question about seed coating. Can you do the coating yourself, or do you have to purchase that way, even on experimental basis?
So it really, the way that Matt Madsen has made this successful is he's got a bit of an engineering brain, and there's quite a bit of technique and adaptive research that must be done in figuring out how to get these compounds bound to the seed, how to get the seed to flow through something, how to get the right coating. It's not something you just pick up with a cookbook. Yeah, you get a seed coater and you work at it for quite a while. So I think the success will come when Matt figures out a lot of the formulas, and then it's passed on to commercial enterprises to do the seed coating. I'm not sure that's something you can do in your garage overnight. He's been working on it for 6-8 years, and making good progress, but he's learning a lot. One of the things that's pretty exciting is because it's hard to seed sagebrush, you can actually agglomerate sagebrush seed and allow it to flow through a broadcast or drill seeder better. So there's all kinds of things, but it's not a simple thing to do.
Thanks. We did get another question as well. It's, can you talk a little bit more about the slide that showed variability in cheatgrass response amongst all sites? There were a couple sites that had higher cheatgrass presence before treatment than after. Can you talk about why you saw that?
Well, the soil climate information basically told us that these are the ones that have the warm, wet falls. So they had a lot of cheatgrass. Some of them also, on certain plots, did not have a lot of perennial grass, like Scipio and Stansbury, or it was patchy. And so that's where we got a lot of the cheatgrass. So these sites tended to be the warmer and wetter ones, warm, wet in the fall or warm in the spring, and in places not having perennial grass. This one, Oniki sagebrush here, this one baffles us. Right down the hill where we burned Wyoming sagebrush. I'm sorry. We got a lot of cheatgrass on the big sagebrush plots here, but just up the hill on the Oniki juniper site, we got very little. That's where they wagged their fingers at me. You know, if you convert this all to cheatgrass. So this is a little warmer and drier than this. This had a little more perennial grass to begin with that resisted the cheatgrass. So it's a combination of these climatic conditions and having a good perennial grass cover that tends to make this sort out. Now, one of the exceptions is 7 Mile. It doesn't have much perennial grass, but it also has very cold springs and falls. It's fairly high elevation, and there's not a lot of cheatgrass there. Walker Butte, it tends to be a well-drained soil and a little drier and doesn't have a lot of cheatgrass. So our climate and perennial grass doesn't explain everything, but it explains some of it. And but I think one of the take-home messages in here is a lot of these sites have potential after fire to get cheatgrass and even after mechanical treatments. So you're better to, if it's a woodland site, treat it early before the trees get too thick. If it's a Wyoming site, manage your grazing, do vegetation treatments to improve the perennial grass component. So I don't have all the answers. Don't have all the answers.
And for the RC and SM sites on that graph that have a higher percentage of cheatgrass before treatment compared to after, do you have an explanation for why that trend was seen in those sites?
Just it's a little bit cooler site, but believe me, RC does have a lot of cheatgrass on the burn. Some of those plots have quite a bit, but it's a little bit cooler there, and so I'm not sure why that happened. But there's a lot there. There's still quite a good potential for cheatgrass there, but it also has a really good perennial grass component on a lot of the plots.
Great, thank you. We got one more question. It says, there does seem to be a pattern of higher temperatures combined with higher precipitation being linked to more cheatgrass growth. Is that a safe statement to make?
If you get that precipitation in the fall, so cheatgrass germinates in the fall, I think that's very easy for cheatgrass to dominate a site, even if you have perennial grasses. But if you get consistent winter precipitation, you're going to get better perennial grass growth too. So you have this area where cheatgrass is best adapted and perennial grasses aren't, where it's kind of warmer and drier, but enough precip either in the fall or spring to get cheatgrass going. You have it where it's cooler and wetter, where perennial grass is really favored. And then you have all this stuff in between that causes these site differences. And then when you come along and burn, you warm it up a little bit and you can get a lot more germination potential. And but the cheatgrass will go out over time if the perennial grasses are allowed to grow and increase in cover. So one of the things we're doing is, I mean, we're watching this experiment. We're getting ready to summarize 10-year after treatment results, and it'll be interesting to see just what happens. What I'm seeing is on the mechanical treatments in the tree expansion sites, the cheatgrass is tending to diminish and the perennial grass is continuing to increase. On the burn plots, it's tending to continue to increase, the cheatgrass is, while the tall grasses are also increasing. So it's going to be a while to see what really happens here, especially on those burn plots.
Thanks so much, Bruce. We don't have any other questions in the queue right now. Rick, do you have anything else you'd want to ask?
Not at this point. I suggest we stand by for just a minute or so to see if other questions come in, and then we'll wrap things up.
Great.
I guess I could say that there was another part to the LCC funded project, and that was looking at some 40 masticated sites and abiotic variables that are related to cheatgrass. And we're just doing the analysis of that, but it's tending to support what we've seen here. Warmer sites, a little bit drier sites tend to get more cheatgrass. Cooler, wetter sites, more perennial grass.
We did get one more question. Are any of the sites excluded from livestock grazing?
All of the sites are excluded from livestock grazing that I reported on in this study. They've been excluded since 2005, 2006. So.
Okay, well, thank you. Thank you, Bruce, for your outstanding presentation here today. And those listening in, thank you for attending today's webinar. A recording of this presentation will be available on our website later this week. If you have questions about the LCC or this research, please feel free to contact myself or John Tull, our science coordinator, or Dr. Roundy. His contact information is available here. Last but not least, we really want to know what you thought of today's webinar. So please take our short 2-minute survey that will appear on your screen as you log off. Your feedback is very important to us, helps us to plan and improve future webinars. Well, with that, I want to say thank you once again to Dr. Bruce Roundy and our participants online here today. We look forward to seeing and hearing from you, and wish you a very good day.
Thank you.